When you look up at the night sky, everything seems so impossibly vast, so distant, and so static. The stars look like they're just fixed jewels in velvet, the nebulae seem frozen in place. But that is the great optical illusion of cosmology.
It really is. The universe is anything but static. It's a constantly flowing, churning, dynamical system, all driven by these immense forces, and the gas, the plasma, the stellar material. It all flows according to rules that we here on Earth usually associate with things like water or air.
Exactly, and that's what this deep dive is all about. It's what happens when you take terrestrial fluid mechanics and you just scale it up to the cosmos. We're talking about astrophysical fluid dynamics. It's the
Physics governing the flow and the equilibrium of massive amounts of matter in space, from the dense core of a dying white dwarf all the way to the incredibly wispy intergalactic medium.
And it's really about how we take the messy reality of trillions and trillions of discrete particles and through these really elegant mathematical shortcuts, simplify it all down to beautiful, solvable equations.
For this one, we've synthesized a genuinely foundational stack of sources. This is really the bedrock of theoretical astrophysics. We've been immersed in the analytical and computational aspects of fluid dynamics, especially as they're applied to stellar structure and gas distribution.
We have. We're drawing heavily on the legacy of theoretical giants like Superman Chandrasekhar, Jeremiah Ostraker, and Mirko Abramovich.
So our mission today is pretty laser-focused. We want you, our listener, to walk away with a thorough,
really intuitive understanding of two big things. First, the fundamental physical assumptions that let us conceptually treat cosmic matter as a fluid, and, just as importantly,
why those assumptions sometimes break.
And second, how those foundational conservation laws lead us directly to one of the most elegant and powerful mathematical models in the entire field, the Emden equation. We're going to show how this single equation, just by changing its geometry, defines the stable, vast structures of stars and massive gas clouds across the entire universe.
Okay, let's unpack this. So, when someone says fluid, my brain pictures something viscous, something dense, something you can pour. How do we make that conceptual leap from a physical fluid on Earth to, say, a nebula containing maybe one particle per cubic centimeter?
Right, and that's the essential question. It really comes down to scale separation and averaging. In classical hydrodynamics, we define a fluid as a continuous medium.
A continuum.
Exactly. This allows us to define macroscopic properties, things like density, bulk velocity, pressure, at every infinitesimally small point in space.
Yeah.
It's an averaging process that basically lets us ignore the micro-scale jostling of all the individual molecules.
So in astrophysics, we're using the same conceptual shortcut to deal with the sheer vastness of it all. If we're modeling the evolution of a spiral arm in a galaxy, we're not trying to calculate the trajectory of every single star and molecule in that arm.
Oh, absolutely not. That would require an infinitely powerful computer. We couldn't even begin to do that. So the power of this astrophysical analogy is realizing that on the scale of, say, a few parsecs, all the individual random motions of particles, what we call the thermal component, can just be averaged out. We look at the mean properties of whole regions of space.
And that shortcut is what opens the door.
It's what opens the door to modeling these immense flows using the comparatively simple rules of fluid dynamics rather than the intractable complexity of particle physics.
And this leads to a really fundamental
insight, a real nugget that applies whether you're studying the water in the Mariana Trench or the gas around a quasar.
It's that the genius of fluid dynamics is that it ignores the microphysical complexity of different systems.
It doesn't care if the particles are neutral atoms or ionized plasma or degenerate electrons, provided only one thing is known.
And that's the equation of state, the EOS.
That's it. If you know the relationship between pressure, density, and temperature for that specific type of matter, the physics becomes transferable. It doesn't matter how the particles interact, only what the resulting pressure is for a given density and temperature. It is the ultimate simplification.
Okay, so with that EOS requirement in mind, what are the universe's main fluids that we actually apply these equations to?
Well, they fall into several pretty crucial categories. The first, and maybe the most familiar, is the
Material that makes up stars. We model their interiors as being in a state of hydrostatic equilibrium, where gravity and pressure are in this perfect, delicate balance.
But even in that static state,
The gas is super dynamic, right?
highly dynamic. It's subject to internal motions like these massive convection currents carrying heat outward, or even low amplitude oscillations, which is a field known as stellar seismology, that we use to probe the internal structure.
But, and this is a critical caveat mentioned in the source material, this standard fluid dynamic treatment is not valid once you get above the star's photosphere. Why does the model break down there?
It breaks down completely because of density. Once you move into the upper atmosphere of the star and into the stellar wind, the gas density just plummets so dramatically that core assumption that the fluid is continuous everywhere is no longer met.
The particles are just too far apart.
Way too far apart to be modeled as a continuous bulk medium.
Okay, so what's the second major fluid category?
That would be the distributed gas. This includes the interstellar medium, or ISM, that you find within galaxies,
And the intergalactic medium, the IGM, which spans the cosmic voids between galaxies. And this is where we really need to recalibrate our intuition about what density means.
Right.
the mean density in our Milky Way, for example, is ridiculously low. It's about 1 particle per cubic centimeter.
One particle. That sounds like basically nothing. A perfect vacuum.
It practically is nothing. I mean, to put that into perspective, that's about 10 to the 6 particles per cubic meter. Now compare that to the air we're breathing right now at normal temperature and pressure on Earth. That is 2.7 times 10 to the 25th particles per cubic meter. The ISM is almost a perfect vacuum compared to terrestrial gas. Yet, over the vast scales we're talking about, we can still treat this gas dynamically as a continuous fluid.
And beyond stars and this diffuse gas, where else do we use fluid dynamics?
Oh, virtually every large-scale flow. We model highly collimated flows like stellar winds and these massive jets that stream from active galactic nuclei. We model the incredibly intricate
Rotational structures of accretion disks that are spiraling into black holes.
Wow.
And we even model the internal physics of dense, exotic objects like white dwarfs and neutron stars.
where the matter behaves as this highly compressible, relativistic, and degenerate fluid.
To make any of these calculations work, we have to rely on this conceptual entity, the fluid element. This is the little parcel of matter we're following. But the definition of what makes a valid fluid element seems paramount, and it brings us right back to that massive density difference you mentioned.
It does. The fluid element is necessary for defining local variables, like density and temperature. For the concept to be mathematically sound, the region we define has to satisfy 2 conditions about its size. First, it has to be large enough statistically.
Meaning,
It needs to contain enough particles to ensure that fluctuations caused by just, small numbers don't throw off our average density reading.
okay, that makes sense. And the second condition is the one that really dictates whether we can even use standard hydrodynamics.
At all. And it all hinges on collisionality.
This is the absolute make-or-break criterion. The length scale of the region we define as the fluid element,
Let's call it Langell, must be much, much greater than the mean free path of the particles, which we call lambda.
And the mean free path is the average distance a particle travels before it smacks into another one.
Exactly, before it hits another particle.
Oh, wait a minute. If the ISM has only 1 particle per cubic centimeter, how can we possibly argue that particles are hitting each other enough for that condition to hold? Isn't the mean free path lambda just enormous in the IGM?
That is an excellent and very challenging point, and it's where the concept of effective collisionality comes in. Well, the mean free path is huge. I mean, it can be light years in the intergalactic medium. The relevant comparison is between the size of our region and that mean free path lambda-less. For systems like massive gas clouds in the ISM, the physical size of the region is often even more immense than the mean free path, sometimes by factors of 100,000 or more. So while collisions are rare
in absolute terms, they happen frequently enough relative to the overall system size to establish equilibrium within that system's typical lifetime.
So as long as a legion is much greater than lambda,
We have a collisional fluid. Why is it so crucial for the math?
because frequent interaction is the only way a system can achieve a state of maximum entropy. This means the particle speed distribution follows a well-defined Maxwellian distribution that corresponds to the local temperature. And this, in turn, guarantees the system has a well-defined pressure and a solvable equation of state.
And if you have to find pressure,
Then you can use the Navier-Stokes family of equations, and you can actually solve the problem.
so what happens when that condition fails? When the system is not collisional?
Well, that's the theoretical disaster. Systems where a raging ball is not greater than lambda are non-collisional. The particle speeds just don't settle into a state of maximum entropy. This describes systems like orbiting stars in a galaxy, or dark matter halos, or even large grains in Saturn's rings.
And the consequence for the theorist is
Devastating. No unique equation
Equation of state can be written.
and no unique EOS means you lose the ability to use that fluid dynamic shortcut.
You lose everything. The solutions describing their motion become
non-unique. They are path-dependent, and the system is effectively unsolvable using standard hydrodynamics. You can't predict the macroscopic behavior from simple conservation laws alone.
So what do you do?
In those cases, astrophysicists have to abandon hydrodynamics entirely and resort to these highly complex n-body simulations, where you're tracking the individual gravitational interactions of millions or even billions of particles, which is, as you can imagine, enormously more computationally intensive.
So the ability to treat a vast cosmic structure as a simple fluid hinges entirely on the particles being, I guess, dense enough to bump into each other constantly, even if that bumping only happens once every few decades.
That's a remarkable testament to the power of statistical physics.
So once we've established that we have a valid collisional fluid, we then formulate the governing equations. And these are based on the
Three fundamental conservation laws: mass, momentum, and energy.
Okay, but before diving into the equations themselves, let's quickly clarify the two mathematical descriptions of motion because this can be confusing. Lagrangian versus Eulerian?
They're simply different perspectives. The Lagrangian description is personal. The reference frame moves with the fluid element. So if you release a weather balloon and you track its position, its temperature, and its velocity for its entire journey, you are using the Lagrangian perspective.
Right.
It's represented by the total time derivative, day of q dt2.
I always think of that as like driving a specific car in traffic and monitoring that one car's speed and direction.
That's a perfect analogy. That's exactly it. Now, the Eulerian description is
observational. The reference frame is fixed in space. It's like a camera on an overpass watching the traffic flow underneath.
You're just watching the cars come and go through a fixed point.
Exactly. You're watching
fluid elements or cars come and go through that fixed point. It's represented by the partial derivative over time plus the advection term partial q, partial t plus vaco plus v cubed.
The advection term, that vecti conable qt, that's the crucial part there, isn't it?
It is, yes, because it accounts for how the bulk flow contributes to the change at that fixed location. Even if the flow is perfectly steady, meaning the partial derivative partial q partial 2 is 0, the properties at that point can still change because a different fluid element is flowing past it.
And linking this back to computation, the sources explain that this choice of perspective really dictates the numerical method you use in a simulation.
Absolutely. Eulerian codes are typically fixed grid codes. They solve the equations within these
stationary grid cells, and they just monitor what flows in and out. Lagrangian codes, on the other hand, which are often called smoothed particle hydrodynamics, or SPH, they use a collection of particles
that represent the fluid elements, and they follow the motion of those particles.
Which makes them great for boundaries and dynamic flows.
Excellent for tracing boundaries and highly dynamic flows, yes.
Okay, so let's start with the simplest law. Conservation of mass. The continuity equation.
In its Eulerian form, it simply states that the rate of change of density in a region over time, plus the net mass flowing out of that region, must equal 0. It's just accounting. If you condense the matter or you slow the outward flow, the density has to increase.
We often hear about incompressible fluids in terrestrial settings. The insight from the source material is that when we say a fluid is incompressible, so do all room is dollars, that doesn't necessarily mean the density dollar is constant everywhere in space.
That's a common misconception,
but a really critical one to clarify. Setting the Lagrangian derivative to 0 means that individual fluid elements maintain a constant density as they travel along their path.
Okay.
But if a fluid element moves from a high-density spot to a low-density spot, the density at that fixed spatial point may indeed change over time. The condition do all of dt equals $0 is what mathematically leads to the defining constraint of an incompressible flow, which is that the divergence of the velocity field, anomalous d, is 0.
Got it. Okay, now let's move to the law of motion, the momentum equation, which is basically Newton's formula for a fluid. For cosmic flows, what are the primary forces driving everything?
Well, if we assume for a moment there are no powerful magnetic fields, which is often a useful simplification, we primarily consider two massive forces, gravitation and the pressure gradient.
And the pressure gradient is always written as negative, nabla p. Why is that minus sign so crucial?
The gradient operator,
nabla p, always points in the direction of the greatest increase in a scalar quantity. So for a pressure field, nabla p points toward the highest pressure.
Uphill, basically.
Uphill, exactly. The force, Ford law, always acts to accelerate matter from high pressure to low pressure, downhill. Therefore, the force due to pressure must act in the opposite direction of the gradient, hence the minus sign. It's the fundamental driving force of expansion.
So So the Lagrangian momentum form is just density times acceleration equals the outward push of the pressure gradient plus the inward pull of gravity. Square nabla P plus nabla P.
That's it. That one equation governs everything from the internal motion of a star to the outflow of a stellar wind.
You know, I love the way the sources break down the momentum flux in the Eulerian form because it helps us conceptually separate two different types of pressure in space, thermal and ram pressure.
Yes, and this is more than just a mathematical distinction, it's a physical one. When you decompose the stress tensor within the full Eulerian momentum equation, the diagonal terms represent the hydrostatic
component. That's the pressure associated with the random motions of particles within the fluid element.
So that's the thermal pressure, that's the heat.
That is the heat, exactly.
And the off-diagonal terms.
Those are the non-hydrostatic terms. They represent the momentum flux associated with the bulk, ordered flow of the fluid element itself. We call this the ram pressure. You can think of it as kinetic energy density.
Can you give us an analogy to make that ram pressure concept really stick?
Certainly. Imagine a massive stellar wind or a supernova remnant expanding out into the interstellar medium. The material is moving at thousands of kilometers per second. The thermal pressure within that expanding gas is huge, but it's the sheer bulk momentum, the ram pressure of that shell smashing into the surrounding static gas that drives the expansion and creates the large shock front that we can actually observe.
So it's the difference between the random jiggle of molecules, which is thermal, and the direct impact of a moving hammer, which is ram.
That's the perfect way to put it.
Okay, the final governing law in this section is the critical role of gravity. Unlike on Earth, where we might just assume Vega is constant,
Gravity is the master sculptor of cosmic structures.
It is the overwhelming force.
Mm.
And since gravity is a conservative force field, meaning no energy is dissipated moving a particle
Around the closed loop, the curl of the force field is zero. The ball times Vegas.
Okay.
This allows us to express the gravitational acceleration as the gradient of the scalar field, which we call the gravitational potential. So big level up.
And that potential is linked directly back to the mass distribution through Poisson's equation.
Modal of Gizeh. This equation is really the mathematical heart of self-gravity. It connects the density distribution directly to the curvature of the potential, normal to Gizeh. The source material highlights some specific, really cool geometry insights derived from this.
Like what?
Well, for a spherically symmetric mass distribution, a profound result holds. The gravitational acceleration at any point depends only on the mass enclosed interior to that point.
That's the famous shell theorem, right?
Which tells us that if you're inside a spherical shell of matter, you feel no net gravitational pull from it.
Exactly. This is the isolation of a local gravitational field in terms of acceleration.
But here's where it gets
Really interesting, because the source material points out that while the acceleration of Vec is unaffected by outside material, the absolute gravitational potential, dp2d2ga, is affected, and that seems counterintuitive to me.
It is a critical and very subtle conceptual distinction. Think of gravity as a giant Russian nesting doll of mass shells. If you're standing on one shell, the shells outside you exert no net acceleration on you because their poles cancel out symmetrically. So the event's unchanged.
But the potential.
Well, the potential is a measure of the total work required to bring a particle from infinity to that point. Every single piece of mass in the universe contributes to that total work. So if you add more mass far away, the outer
Shells of the Russian doll, the total energy required to build the entire system increases.
Oh, okay.
Therefore, the absolute value of the potential deepens or decreases due to the presence of that exterior mass.
So the overall energy state of the system changes, but the force experienced locally, the acceleration is constant.
Precisely. The acceleration is determined only by the gradient of the potential, the slope of the hill. And since the external mass distribution is spherical, it creates a constant background to the potential that doesn't change the local slope. The potential difference between two nearby points remains unchanged even when you add that distant mass. It just shows how mathematically complex even simple self-gravity truly is.
Okay, so we've established mass conservation and momentum conservation. We've coupled them with self-gravity.
But as we discussed briefly earlier, if we rely on the ideal gas law, which is Propto-Chak now, we've created a system with more unknowns than equations. We've got density, velocity,
And now temperature, we need a third independent equation.
Right. This is known as the closure problem in fluid dynamics.
Yeah.
If we don't know Jolars, the system is mathematically unsolvable. The traditional solution is to introduce a full energy equation, which accounts for internal energy, work done by pressure, heat transfer, all of it. But that full equation is computationally horrific for many
So we use the shortcut, the crucial shortcut to bypass that complexity. The barotropic equation of state. This is where we assume that pressure is a function of density only. So PPQ.
By assuming a barotropic condition, we are implicitly assuming a relationship between density and temperature, and that effectively closes the system mathematically. This assumption just drastically simplifies the complexity, and astrophysicists rely on two primary barotropic cases that come from this shortcut.
And the first is the isothermal case.
That's PP
Propto-Horo. This assumes a constant temperature throughout the entire system, meaning the medium is in perfect thermal equilibrium. It implies that any energy input or output is immediately
and perfectly balanced by some cooling or heating process which maintains a steady temperature.
And this models gas clouds where radiation is super efficient, acting like a thermostat.
Exactly. And the second case is the adiabatic case,
which is PPR.
Right. This models systems where compression or expansion happens so quickly that there's just no time for heat exchange with the surroundings. It assumes reversible internal changes and is useful for modeling dynamic events like sound waves traveling through a star or the rapid pressure changes deep within a stellar core. But it does neglect irreversible dissipation like viscosity or shocks.
But sometimes, especially when you're modeling stellar evolution or the detailed collapse of a star-forming core, you have to confront
the full picture. You need the energy equation, and specifically the terms that govern how energy is transported and lost.
Yes, the full Eulerian energy equation is a beast.
But its most physically relevant terms are those related to energy loss, or what we call the critical cooling term, cool dollars. And this leads us to the physical processes of energy transport in space.
Let's start with the dominant heating mechanism in the ISM cosmic rays.
Cosmic rays are just highly energetic particles, mostly atomic nuclei stripped of their electrons, that have been accelerated to relativistic speeds by supernova shocks and other violent events. When they penetrate the interstellar medium, they cause ionization. The excess kinetic energy of the ejected electrons is then rapidly converted into heat via collisions. So the heating rate is fundamentally proportional to both the cosmic ray flux and, logically, the density of the gas that's available to be ionized.
Okay, so
moving to cooling and transport, the first mechanism is conduction.
Conduction is heat transfer via physical contact, and it requires free, mobile particles. It's defined by
heat flux dropped to an apple today. Because astrophysical plasmas are generally so tenuous, conduction is usually pretty negligible.
But not always.
Not always. In extreme environments, like the dense, degenerate electron fluid inside a white dwarf, or in the extremely thin, hot gas behind a powerful supernova shock front, the electron speeds are so high that conduction actually becomes the dominant heat transfer mechanism.
Then there's convection, which is transported by bulk fluid motion.
Right, and convection is driven by the gravitational field responding to temperature gradients. If a small parcel of gas is warmer than its surroundings, it becomes buoyant and rises, carrying its thermal energy with it. This process is absolutely vital in stellar physics. It drives energy transport in the cores of massive stars and through the outer envelopes of lower mass stars like our Sun.
And the final, most complex, and often the most dominant mechanism is radiation.
And radiation has to be split into two very distinct regimes.
First, you have the optically thick limit. This happens deep inside dense objects, like a star, where the mean free path of a photon is minuscule, maybe only a few centimeters.
So photons are just constantly being scattered and reabsorbed?
Constantly. It's a diffusive process where energy slowly leaks outward, but the memory of the original emission process is completely wiped clean. This is why we can only ever measure the temperature of a star's visible surface, the photosphere, because that's the point where the medium finally becomes optically thin.
Which brings us to the optically thin limit. This describes low-density gas like nebulae or the IGM, where photons just escape directly into space, carrying energy away and causing cooling. And this is where four specific emission mechanisms dominate.
Let's run through those. The first is recombination, where free electrons find and recombine with ions, releasing energy. The second, and this is crucial for high-temperature plasma, is bremsstrahlung, or breaking radiation.
Bremsstrahlung is generated when a free electron flies past an ion and is
Accelerated or braked by the ion's electric field, causing it to emit a photon. The cooling rate is proportional to $no squart now mpg. What does that $2 dependency tell us physically?
That $Z term is key. $Z is the atomic number, so it's the charge of the ion. Since the force is proportional to $Z, the radiation emitted depends on the square of the acceleration, the cooling rate depends on $Z too. This means that if you have even a tiny amount of heavier element contamination, say a little bit of iron where Z is $26 rather than just hydrogen where $Z is 100, cooling rate just skyrockets.
So heavier elements are exponentially more efficient at shedding energy via Bremsstrahlung.
Exponentially. Even trace metallicity radically alters the cooling efficiency of hot plasma.
Wow.
But the most effective cooling process for nebulae and gas clouds is the third one, collisionally excited atomic line radiation.
And why is that the heavy hitter?
Because it acts as the universe's thermostat. In cooler regions, specifically around 10,000 Kelvin, there isn't enough energy for electrons to excite the fundamental transition.
in hydrogen. But the kinetic energy of the electrons is sufficient to excite the fine structure energy levels in heavier, more complex ions.
Which ions are we talking about here?
We're talking about trace elements like singly or doubly ionized oxygen, more like plus, carbon or nitrogen, all on $1+1. These ions have very closely spaced energy levels. A low energy electron collision can easily boost an outer electron into the next energy level.
And then it just drops back down.
Almost instantaneously, it drops back down, radiating away the energy as a specific spectral line photon that just escapes the optically thin cloud. This process is so efficient that it keeps the ISM temperature remarkably stable around 10,000 K.
So it's basically thermal regulation, and the heavy elements are the radiators.
They are the efficient radiators for that specific temperature window, precisely. And finally, the fourth contribution is molecular collisions, which is dominant in the very coldest regions around
100 Kelvin. Collisions convert kinetic energy into rotational and vibrational molecular energy, which then radiates away, leading to the collapse and cooling required for star formation.
Okay, so when we synthesize all that complexity, what's the simplified, often used rule for low-density cooling?
For optically thin, low-density cases, the synthesis reveals that the cooling rate per unit mass is often simplified to be linearly proportional to the gas density, and this simple linear relationship is a massive computational relief. It allows simulators to model cooling without having to track every single radiative transition.
All of this understanding of pressure, density, and energy transport leads us back to the most fundamental stable state we can have, hydrostatic equilibrium.
This is the mathematically simplest state you can imagine. We just assume the system is static, so basically easy rider. And the momentum equation collapses to the simple balance between the pressure gradient and gravity. $1 in Nabla, P, Nabla today.
And our sources use this exact condition to model the isothermal slab, an infinite static sheet of gas. This sounds like an abstraction,
But it models real physical structures.
It does. It can model structures like the layer of gas shocked between two colliding molecular clouds, or even the thin, settled gas plane of a galactic disk.
Since it's isothermal, we use the barotropic condition Raposo paneled. Solving the simplified momentum and Poisson equations yields this beautiful density profile.
and that profile is Proto-Proctor-1 course, where CSI is the height from the central plane.
Right, the profile is bell-shaped. It peaks in the center and then smoothly drops off towards zero. The $Z return gives the characteristic scale height, and that's determined by the gas temperature and the gravitational constant. So a perfectly stable, self-gravitating structure.
We can also relate this back to a more everyday example, the Earth's atmosphere. If we model it as an isothermal atmosphere with constant gravity.
In that approximation, where we assume $Z is constant, the density decreases exponentially with height. Proto-E, GRTZ, and this dramatic
Exponential decay explains why the air density thins out so rapidly as we go up.
Which is precisely why major observatories, like the ones on Mauna Kea in Hawaii, place their powerful
Telescopes at 4.2 kilometers. They're just moving above the majority of the gaseous medium. They're relying on this exponential density decay to maximize light clarity and minimize atmospheric absorption. It's a direct application of the hydrostatic equilibrium principle we just analyzed.
So we saw that simple hydrostatic equilibrium, like the isothermal slab, can give us stable structures. However, when we try to model a spherical star using that same isothermal condition, we run into immediate mathematical problems involving infinite mass, which we'll get to in a second. And this leads us to the more sophisticated barotropic approximation known as the polytrope, and the resulting model developed largely by Chandrasekhar, the Lane-Emden equation.
So why is the polytropic approximation, PP equal 1 plus 1?
Why is that particularly useful for modeling stars?
Well, stellar interiors are just these complex mixtures of radiation pressure, ideal gas pressure, sometimes degenerate pressure.
Modeling the energy transport that we just talked about perfectly is intractable. So a polytropic EOS provides a robust way to relate pressure to density that kind of encapsulates the dominant energy transport mechanism.
Okay, so it's a proxy.
It's a very good proxy. For instance, a polytropic index of 1 idealisticity 3Ps is a very good approximation for massive stars that are dominated by radiation pressure, while on $1.555 models, stars dominated by convection. It's a mathematical tool that efficiently captures the physics of the system.
Now, assuming spherical symmetry, we combine the momentum equation and Poisson's equation using this polytropic EOS. We introduce some normalized variables for potential and radius, and we arrive at the classic second-degree
Emden equation.
Which is a beautiful piece of physics. It's essentially a second-order nonlinear differential equation that, when you solve it, describes the entire density and pressure
profile of a self-gravitating spherical body of fluid, a star from its core all the way to its surface.
And the physical constraints, the boundary conditions, are all set at the center.
Yes. For a real star at the center, where the normalized radius is 0, the normalized potential of beta is set to 1. That represents the maximum density and pressure. And the derivative, the dot sheet, is 0, which just reflects that the pressure gradient is 0 at the very center due to symmetry.
And then you just solve it outwards.
You solve it outwards until theta reaches 0, and that point defines the physical radius of the star.
Although most of these polytropic indices require a computer to solve them, our sources highlight 3 analytic solutions for the spherical case that offer these really profound physical insights.
All right, let's start with the simplest. $1. The solution is 1/16 by 2 down. And when we trace where that theta goes to 0, we find a very sharp finite radius. This models a body of uniform density, which is,
physically unrealistic for any fluid structure, but it's mathematically simple and self-contained.
Okay, so moving to $1, this one is defined by the sinc function.
Thanks to 1, this solution is fascinating
because the density profile decreases monotonically from the center and reaches 0 exactly when they call pi. This defines a perfectly self-limited finite structure. It's a star model that has a clear, sharp boundary.
And then there's the famous 1/5 solution, often called the Emden standard solution, which is where things get conceptually weird.
They do. 1554 gives the solution 35.5, 1 plus 13 by 2. When you analyze this, you see that theta doodle only approaches 0 as theta doodle approaches infinity. So this polytrope mathematically describes a stable, self-gravitating sphere that extends indefinitely into space. It has an infinite radius.
An infinite star. Does it also have infinite mass?
No, and that's the surprising part. Despite the infinite radius, this configuration is one of the special cases where the total mass remains finite.
The density drops off so rapidly with radius that the total mass actually converges to a finite value. It's a stable, infinitely sprawling configuration, but it only contains a finite amount of material.
This Eta-Doodle model serves as a great lead-in to the limit where the polytropic index tends to infinity, which models the isothermal sphere.
Right. As light goes to infinity, the polytropic EOS approaches the true isothermal proctorowinic limit. When you try to model a self-gravitating gas sphere using this EOS, the result is that the structure has to have an infinite radius, similar to the Enedon 505 case.
But there's a problem.
There's a deeper problem. Unlike anti-wide, the isothermal sphere runs into an issue where, unless you apply some very specific non-physical boundary conditions, the system results in infinite mass.
So if a self-gravitating isothermal sphere has infinite mass, it means a spherical cloud in thermal equilibrium just can't exist unless something is stopping it from extending forever.
Precisely. A real physical structure has to be truncated. An isothermal sphere can only be in hydrostatic
equilibrium if it's placed in an external medium that imposes an appropriate confining pressure. If that external pressure is too low, the sphere is unstable and it just collapses.
And these truncated
structures, they have a powerful real-world application.
They do. These structures are known as Bonner-Ebert spheres, named after the scientists who studied their stability limits. And they're now the standard, extremely effective model used to describe the structure and mass limits of dense gas cores in molecular clouds, the very regions where star formation begins.
So they tell us how big a cloud can get before it collapses.
They tell us exactly how large and massive a cloud core can be before its own self-gravity overcomes its internal thermal pressure and it collapses into a protostar. It's a clear case of a mathematical failure leading to a critical physical insight about stability.
Okay, that's incredible. Now let's pivot the geometry. We're going to move from Chandrasekhar's sphere to the work done by Ostrander, who studied the cylinder, forcing us to shift to cylindrical polar coordinates.
And this change in geometry just radically
alters the outcome. The difference between a spherical and a cylindrical structure under self-gravity is profound, particularly when you look at the behavior at large radii.
And the key finding is that unlike the
spherical polytropes, which struggle with infinite radii and potentially infinite mass, cylindrical polytropes have finite radii and finite masses for all the relevant indices.
This is a major structural difference. For instance, the solution for the inequally cylindrical polytrope is the Bessel function, J dollars, which rapidly drops to zero at a finite radius. This means cylindrical gas structures are inherently more compact and self-limited than their spherical counterparts.
Our sources also highlight how the density changes as the index story increases in the cylinder model.
As none increases, the structure becomes more centrally concentrated or contracted in the inner regions, but it simultaneously becomes more extended in the outer regions.
Yeah.
But critically, the density still always hits zero at a finite distance. The problem we saw with the spherical 55.5 case just doesn't manifest in the cylinder geometry.
Okay, so the ultimate test is the isothermal limit for the cylinder when no anomaly goes
To
to
infinity. This is where Oestreicher provided a unique and highly applicable insight.
The isothermal cylinder is mathematically unique. In direct contrast to the spherical case, the isothermal cylinder
does form a stable, physically meaningful structure. Most importantly, the total mass per unit length within a cylinder tends to a finite limit as the radius approaches infinity.
Wait, so an infinitely extended cylindrical structure, which could perfectly model, say, an entire galactic spiral arm or a long molecular filament, it contains a mass per unit length that is mathematically constrained and finite.
Exactly. And this mass limit isn't arbitrary. It depends only on the temperature and the mass per particle. It's a fundamental physical constraint that the cylindrical geometry imposes on the material.
That's incredible. Can we put a physical scale on that? Can we calculate it?
We can. For gas composed of neutral hydrogen, which is a reasonable proxy for cool gas filaments, at a cold temperature of 100 Kelvin, Oestreicher's solution predicts a mass per parsec length of approximately 400 solar masses.
So 400 times the mass of the sun.
Contained in every 3 light years of filament length.
Yes, and that number is entirely plausible for large-scale structures like spiral arms or dense, elongated molecular filaments.
It's a perfect example of elegant mathematics dictating the observable scale of a cosmic phenomenon.
Finally, we should touch upon the generalization of this, where Bromwich studied the nth degree Lane-Emden equation to describe geometries beyond just the sphere and the cylinder.
Right. Abramovich formalized the general equation to incorporate spatial symmetries of different degrees, non-levers. So, for example, $1 is related to extremely thin self-gravitating accretion disks, almost two-dimensional sheets. 101 is Oestreicher's cylinder, and 1 Crow is Chandra-Sekhar sphere.
And did he find a solution that mirrors the conceptual strangeness of that monofive sphere or the isothermal cylinder?
He did. He identified a special analytic solution for the polytropic index where
$1 n plus 3, and I went 1. Just like the nth of a sphere, this configuration extends to infinity. However, he showed that this special generalized solution can be shown to retain a finite
total mass, regardless of its geometric dimension 1 to left.
So across every geometry we can model, this one specific index defines the transition point, a structure that is mathematically infinite in its extent, but physically finite in its content.
It demonstrates that the transition from a sharply bounded and stable structure to an infinitely extended but still stable structure is a highly specific function of the geometry and the assumed equation of state. The universe only permits certain stable configurations, and the Lane-Emden equation is the filter.
So this deep dive has really shown us how the universe's largest, most seemingly static flows are governed by just a handful of fundamental physical laws. We started by defining cosmic matter as a continuous fluid, a simplification that only works if the matter is collisional, which gives us that crucial, unique equation of state.
We then connected the conservation laws of mass and momentum with the non-negotiable force of gravity through Poisson's equation, and we realized that the system of equations has to be closed.
often by using the barotropic assumption, a necessary simplification to bypass the immense complexity of calculating every heat transfer and radiation process.
And finally, we saw the incredible
Mathematical elegance of the Lane-Emden equation. It's an equation that, just depending on its index and its geometry, can define everything from a dense, strictly bounded stellar core to a sprawling, infinitely extended molecular filament.
The central synthesis here, I think, is that the ability of theoretical astrophysics to accurately model these vast, tangible structures, stars, gas clouds, spiral arms, relies entirely on making these very crude, simplifying assumptions. These polytropic and barotropic shortcuts convert otherwise unsolvable systems into these elegant, closed equations that actually do a great job of predicting cosmic reality.
And that profound interplay between infinite scale and finite constraint leads us to our final provocative thought.
We learned that the structure of an infinitely extended object, like the isothermal cylinder or that specialized Abramovich polytrope, can be fundamentally finite in terms of its total mass.
And this raises a fascinating question. We often assume large cosmic structures are unbounded, but if geometry and temperature alone impose finite limits on the mass per unit volume for these infinite configurations, what other seemingly boundless cosmic phenomena, maybe the structure of galaxy clusters or the distribution of matter in the great cosmic void, might be governed by hidden finite mathematical limits that depend only on simple physical properties like temperature and particle mass?
Something for you to mull over the next time you look up at the